An algorithm is a set of well-defined, step-by-step instructions designed to perform a specific task or solve a particular problem. The concept of algorithms is fundamental to computer science and mathematics, but its applications extend to various fields such as biology, economics, engineering, and more. Origins and history. The term algorithm comes from the name of the Persian mathematician, Muhammad ibn Musa al-Khwarizmi, who lived during the 9th century. His work on solving mathematical problems laid the foundation for what would later be known as algebra. The Latin translation of his name, algorithmi, is where the term algorithm is derived from. Al-Khwarizmi's book, Al-Kitab al-Muqtazar fi Hisab al-Jabr wal Muqabala, the compendious book on calculation by completion and balancing, played a crucial role in the development of algebra and introduced systematic methods for solving linear and quadratic equations, which can be seen as early examples of algorithms. Basic characteristics. An algorithm, at its core, must satisfy several key characteristics to be considered valid. 1. Finiteness. An algorithm must always terminate after a finite number of steps. If it doesn't, it could lead to an infinite loop, which means the problem won't be solved. 2. Definiteness. Every step in an algorithm must be precisely defined. The instructions should be clear and unambiguous, so they can be followed exactly. 3. Input. An algorithm must have 0 or more inputs, which are the initial data provided to the algorithm for processing. 4. Output. An algorithm must have 1 or more outputs, which are the results of the processing performed by the algorithm. 5. Effectiveness. The steps of an algorithm must be basic enough to be performed, in principle, by a human using paper and pencil. This means that each operation must be simple and feasible. Types of algorithms. Algorithms can be categorized in various ways based on their purpose, approach, or complexity. Some common types include 1. Brute force algorithms. These involve checking all possible solutions to find the correct one. While simple to implement, they are often inefficient for large problems. An example is the algorithm for solving the traveling salesman problem by checking every possible route. 2. Divide and conquer algorithms. *. These break down a problem into smaller subproblems, solve each subproblem recursively, and then combine the solutions to solve the original problem. A well-known example is the merge-sort algorithm. 3. Greedy algorithms. *. These make a sequence of choices, each of which looks best at the moment, with the hope that the overall solution will be optimal. An example is Dijkstra's algorithm for finding the shortest path in a graph. 4. Dynamic programming algorithms. These solve problems by breaking them down into simpler subproblems and storing the results of these subproblems to avoid redundant computations. The Fibonacci sequence calculation is a classic example. 5. Backtracking algorithms. These involve trying different possibilities and undoing them if they lead to a dead end. The Sudoku puzzle can be solved using a backtracking algorithm. 6. Randomized algorithms. These use randomness as part of their logic, sometimes to make decisions or to reduce the average time complexity. An example is the quicksort algorithm, where the pivot element is chosen randomly. Algorithm complexity. Understanding an algorithm's efficiency is crucial, especially when dealing with large datasets or problems that need to be solved in real time. Algorithm complexity is typically analyzed in 2 aspects. 1. Time complexity. This measures the amount of time an algorithm takes to run as a function of the size of its input. It's usually expressed using big O notation, which provides an upper bound on the time. For example, an algorithm with a time complexity of O, n, scales linearly with the input size, while one with O, n squared, scales quadratically. 2. Space complexity. This measures the amount of memory an algorithm uses relative to the input size. Like time complexity, it's also expressed in big O notation. For example, an algorithm that uses O(1) space is said to have constant space complexity, meaning the space it uses doesn't depend on the input size. Applications of algorithms. Algorithms are ubiquitous in our daily lives, often operating behind the scenes in technologies we use every day. 1. Search engines. Google's search algorithm ranks web pages based on relevance and other factors, using complex algorithms like PageRank. 2. Cryptography. Algorithms such as RSA and AES are fundamental to securing communications in the digital world. 3. Social media. Algorithms decide what content is shown in your feed, which ads you see, and even whom you might want to connect with. 4. Finance. Algorithms are used in high-frequency trading, fraud detection, and risk management. 5. Medicine. Algorithms help in diagnosing diseases, analyzing medical images, and personalizing treatment plans. 6. Machine learning. Algorithms power everything from recommendation systems on Netflix to self-driving cars. Ethical considerations. While algorithms can greatly enhance efficiency and decision-making, they also raise ethical concerns. Algorithms can perpetuate bias, especially if they are trained on biased data. This can lead to discriminatory practices, such as in hiring processes or criminal justice systems. Additionally, algorithms used in social media can create echo chambers, reinforcing a user's existing beliefs and potentially leading to polarization. In summary, algorithms are the backbone of computer science and play a crucial role in a wide range of fields. Their proper design, analysis, and ethical application are essential to solving complex problems efficiently and responsibly. As technology continues to advance, the importance of understanding and developing algorithms will only grow,